All right. Hey, AP Chemistry. So I'm going to be walking through some of the sample problems in our Unit 8 Important Information Part 1 on acids and bases. We're going to jump all the way to just a little bit reminder about calculating pH. Again, make sure that you've done the questions on page 9, so 1 through 8, calculating pH from H plus and OH minus, and POH and concentration of H plus and concentration of OH minus. I'm going to jump all the way to sample problem number 11. This is a nice refresher on how to calculate equilibrium concentrations and how to calculate pH for a weak acid if I'm given its Ka. So this is for weak acids. pH. Remember, if I'm a strong acid, and that's why I said that's on page 9. If I'm a strong acid or a strong base, I could use the concentration of the acid or base directly to solve for pH because it dissociates 100%. But for a weak acid, it does not dissociate 100%. So I need to do more work. I need to do an ice table to solve for the equilibrium concentration of H plus, and then I could plug that into my negative log to get pH. So it says find the pH of a 0.2 molar solution of HNO2. This is nitrose acid. Ka is 4.6 times 10 to the minus fourth. So the first thing you should always do is write an acid dissociation equation. And I like to do the simple one where I break HNO2 into H plus and NO2 minus. H plus, which is my proton, and NO2 minus, which is the nitrite ion. All right, so this is my acid dissociation. And again, H plus always breaks off of some A minus, okay? And then now I gotta figure out what's going to be my concentration of H plus at equilibrium. Well, the only way I could figure that out is by using an ice table. So I'm going to set myself up an ice table. Zooming out. This is the procedure for calculating the pH of a weak acid. You need to do an ice table. Always, always, always. So splitting this up. Notice how I don't include water ever. I start with 0.2 molar. I've been using a lot of 0.2 molar, but it doesn't matter. You're going to see that all of them are going to have different pHs no matter what the initial concentration. And then initially I have 0 H plus and 0 NO2 minus. Then everything is beautifully 1-to-1 mole ratio. So minus X plus X plus X, 0.200 minus X, X, and X. And if I wanted to write the Ka expression, the Ka expression is always going to be H plus A minus all over HA. So I got H plus NO2 minus all over HNO2. That is how we write a Ka expression. And that is also just how we write an equilibrium expression. An equilibrium expression is products over reactants. All right. Now I'm going to plug in these values, and I already know the value for Ka. It's 4.6 times 10 to the minus fourth. That's small. And we've done so many problems like this by now in Unit 7 on what do I do if I have a small K value. And you're going to see again that I could make some assumptions and we don't do quadratics. So I'm going to write the Ka expression in terms of X. I got X, 0.200 minus X, and it equals 4.6 times 10 to the minus fourth. Well, we don't need to use quadratics in AP Chemistry too much or at all. And so this X in the denominator would make us use quadratics if I had to. But since this value is very small, we could make an assumption. We could say X is approximately equal to 0 since Ka is less than 1 or very small, which makes my calculation a lot more manageable. So now if I want to solve for X, and X gives me my concentration of H plus at equilibrium, I'm going to multiply 0.2 times 4.6 times 10 to the minus fourth. So 0.2 times 4.6 times 10 raised to the minus fourth. I multiply 0.2 times that. And then that's going to give me X times X, which is X squared, equals this number, 9.2 times 10 to the minus fifth. And so now I got to do the square root of both sides. So second square root, second answer, I get X equals I didn't show all my work. All my work's on the calculator. X equals 0.00959 molar, because these values are going to be in concentration. I know I throw in the value, but I know that this value of X needs to be in molarity because it's an equilibrium concentration. So my value of X is equal to my concentration of H plus. I don't need to worry about NO2 minus or HNO2 because the question asks about pH. And remember, pH is going to be equal to the negative log of H plus concentration. Now I know my H plus concentration, so all I got to do is take the negative log of this number. So pH is equal to the negative log of 0.00959, and this will be my pH. Negative log of second answer, I get 2.02. 2.02. That is my answer for this question. My pH for this weak acid is going to be 2.02 if I have 0.2 molar of it. So that is how you solve for the pH of a weak acid. You need to use an ice table, solve for X. Your value of X is going to be your concentration of H+. I wanted to walk through number 12 before I end this video. We started a bit of this in class, or if not, I have it here. For a base, we could do the exact same thing, except X is equal to my concentration of OH minus. So I know I wrote a lot here. What's most important is to recognize that in NaC2H3O2, we have Na plus and C2H3O2 minus. A minus is my conjugate base. We don't worry about the plus. If I give you a salt, and I give you a Kb, and the Kb is going to, I didn't specify, but the Kb is for the Kb of C2H3O2 minus, right? I'd probably specify that better. I need this base dissociation equation. I take my base, I add it to water, I get a conjugate acid, NOH minus. So I'm going to say that again. If I have some salt, this is known as a salt, this is sodium acetate. It has Na plus and C2H3O2 minus. On a previous page, we did work with acetic acid, and we had C2H3O2 minus, and that's a conjugate base for acetic acid, HC2H3O2 minus. Sorry, it's HC2H3O2. This conjugate base can do some work in water in which it produces OH minus as well. And so here is the base dissociation. I have my base, which is some B minus, plus H2O, gives me HB, or HC2H3O2, plus OH minus. We talked about the base dissociation on page 3 of our notes right there. B plus H2O is HB plus OH minus. So we've seen a base dissociation equation, but we haven't written too many of them yet. And so now I have one written here. Don't worry about this top one. This top one has sodium acetate that breaks apart 100% because it's an ionic compound into sodium plus and acetate minus. And so now that I have my acetate into water, right, this is aqueous now. Now I have it in water. It's going to react with water. Water is going to act as an acid, and this is my base. It's going to give an H plus as C2H3O2 minus. And I'm going to get HC2H3O2 and OH minus. And this Kb is this Kb expression. I have HaOH minus all over B minus. And so just to walk you through this, and you could write this if you don't have in your notes, in this dissociation equation, I'm going to be able to get my equilibrium concentration of OH minus, and I could relate that to H plus. If I take the negative log of OH minus, that gives me POH, and then I know that pH plus POH is equal to 14. So if I take the negative log of this value of X that I get at equilibrium, which is just the same way as we did in sample problem 11, if I get the equilibrium concentration, I take the negative log of that, that's going to be POH. If I subtract 14 from it, that's going to be pH. And so I did that. I gave you an initial concentration, I solved all of this, I plugged it into my Kb expression, and I got this number, 5.5 times, oh, that's actually equal to the Kb. Then I solve for X. In doing all the math, I got the value of X is equal to 7.45 times 10 to the minus 7th molar. that's actually equal to my concentration of OH minus. If I take the negative log of that, and I didn't get a chance to finish this, this is the value of X I got for this equation. So if I take the negative log of this, negative log of 7.45 times 10 raised to the minus 7th, my POH is 6.13. So I'm going to write that on the side. My POH is equal to 6.13. If I want my pH, I got to subtract 14 from that. My pH will be equal to 7.87. Still basic. pH plus POH equals 14. So this one's a little bit more involved. If I have a base dissociation and I want the pH, I have to write my base dissociation. I get my value of X, which is my concentration of OH minus because it's a basic solution. Bases produce OH minus in solution. I'll get my POH, which I did. If I take the negative log of the equilibrium value of X that I get, that's going to be my POH. Because taking the negative log of OH minus is POH. I'm not going to get pH. pH is negative log of H plus, but there's no H plus that's produced here. And so now that I have my POH, if I subtract it from 14, I'll get my pH. Now, I know I just said that no H plus is produced here, but don't forget that it's somewhere in the water. There's a water dissociation, and this will probably go back and forth, and I'll have maybe this will break apart into H plus and OH and C2H3O2 minus over here. So it's hard to see that H plus is somewhere in here, and I could figure it out from the relationship between OH minus and H plus. Remember, in our earlier notes, we have KW, which says that the concentration of H plus times the concentration of OH minus has got to equal 1.0 times 10 to the minus 14th if I'm in equilibrium with water dissociation. So that's why we know that taking the negative log of that, pH plus POH is equal to 14. So it's a little bit more involved. Got to get your OH minus, negative log of that, that's POH, subtract 14, that's pH. All right, so this was a video on doing weak acid, weak base dissociations. My next video will talk a little bit more about percent dissociation.